Welcome, everyone, to this evening's lecture in the 2021 Follow the River lecture series hosted by the Hudson River Maritime Museum and sponsored by Rondat Savings Bank. I'm Carla Lesh, Collections Manager and Digital Archivist for the museum. Steve Woods, the museum's Education and Solaris Charter Coordinator, and I will be your hosts this evening. So this evening's lecture is with Frank Almquist as he presents his new book, Building the Ashokan Reservoir.
Okay, this is a map of the valley, starting with the UND Railroad going through West Hurley, Ashton, down to Brown Station. And these communities are about 5 miles apart. And I looked at some old topographical maps of the area. This map is from the late 1800s. And the topography is pretty much right around 500 foot above sea level, maybe plus or minus 20, 25 feet. But the Esopus flows through here and the Beaver Kill. We'll look at that. And so the area is basically a flat basin, and the people live there in these hamlets, and they had really a self-supporting lifestyle. There were farms, boarding houses were all over the place. The summertime, people from New York City would come up and spend a week or so and go back to the city again, and all dressed in finery. I think there's a couple of postcards I know in the book. I have some wonderful ones of a gang of people waiting at the station for the UND train to take them down into Kingston. Logging and sawmills and tanneries, everything you needed to live in that area without having to leave much. A lot of dairy farms, so they had milk, they made cheese. The hamlets had phones, not in every home. The phones were primarily in the general stores, and everybody had electricity. And they had to all be out, and by 1913. So this is West Hurley, a bunch of images of that. They're just great old little communities. The lower one here, they had bluestone sidewalks, but the dirt roads. You see the nice grooves from all the wagon wheels. And almost every home was a 2-story home with a wood stove in the middle. And you probably remember those from your years gone by. Brown Station got a big post office. There were some larger homes. Some of these people's need was a judge. And the Bishop's Falls Bridge, covered bridge, and the waterfall here, and there's a mill back there. A blind man ran the mill. And Ashokan and Broadhead were getting out in the middle of the valley. Not a lot happening there. Ashokan had a little railroad station, and there was a big bridge down in the lower part here that crossed the Esopus. West Ashokan was probably the largest of the communities. You can't find any hamlet census. They only took the census by towns. So they had no idea how many people were in each, but I'm guessing from looking at the size of the community, West Ashokan probably had 1,000, maybe 1,500 people in the late 1900s, before early 1900s, before the people had to move out. So put it into a timeline, the Board of Water Supply in 1899 said, we've got to look at where we can put this dam. We need water in the city. They were actually running out of water. They didn't have enough from the aqueducts and the reservoirs that they had provided at the time. And then in March of 1900, the report came back, well, the Esopus Valley was the best choice. Now that's only about 6-7 months. You know darn well they didn't have drones or airplanes to go over and survey that. But there was a group called the Ramapo Water Company. You can find it written in books a lot, where they were going to be a bunch of businessmen were going to build a dam up here and sell the water to New York City at so much a gallon. Thought they'd make all kinds of money. Well, New York City started going through the numbers and said, sure, you're going to make a lot of money, and you're going to starve us like crazy with water. So they said, no, we're going to take over. So they basically went to the legislature, and the legislature put the Ramapo Water Company out of business and gave okay to the government of New York City to build a reservoir. So construction contracts were awarded in September 30th, and September 9th, some years later, the dam was sealed, and the western basin was collecting water. That water was used to feed the aqueduct and test the sections of the aqueduct as it was built sequentially. And then in June 24th of 1914, all the steam whistles blew for an hour. Everything was powered by compressed air or steam on the whole project. And then potable water was released in 1915, and you can't see the bar, but it's in December 16, the reservoir was full. So that happened. Now, Boyceville, West Hurley, Ashokan, and West Ashokan were all moved. The others were abandoned. And the contract said everything has to be cleared within that 12 square mile area. So it amounted to be a lot of buildings and outbuildings, churches and sawmills. The biggest problem, well, actually there were two large problems. One very lightly discussed was cleaning all the privies. There's a little bit of discussion about that in Last of the Handmade Dams by Bob Studing. But the other problem was finding all the bodies, 40-some cemeteries, and 2,600 bodies had to be moved. And a lot of bodies didn't have any claimant. So they were moved to a Bushkill cemetery. And then I have a picture of that Kate McLaughlin took for me. That's in the book. And then the 13 miles of UND track had to be moved out of the basin up to where it is today. So for record keeping, the Board of Water Supply had surveyors. They surveyed every property dimensioned and took photos of every single structure. When I first came to Kingston many years ago, I wanted to get a permit to fix the reservoir. And the Board of Water Supply had an upstairs office space. I don't remember where it was. All I remember climbing long stairs, and there were files, 5-drawer file cabinets full of these photographs. I asked what they were for. Nobody knows where they went, but it would have been great to have some of them. This is a picture I just happen to have. Now, these are the lead engineers, Freeman, Waldo Smith, Stearns, and Burr. Freeman was a well-known contractor consultant with the water supply for many years. Waldo Smith graduated MIT, and he kept going back and forth to school. But when he was 15, he worked on water supplies in the town in Massachusetts. And he worked for the Aqueduct Commission, part of the water supply, and they promoted him to chief engineer on this project and really uses knowledge quite successfully. Stern and Burr were both educators. They ran civil engineering departments, one at Columbia and one at Rutgers. So they had the technical background to make sure all this stuff happened properly. Now this is a good chart that shows where things are. Whoops. Trying to get this pointer moved. The blue line is Esopus Creek. The other blue line that comes down through here is the Beaver Kill. Now this is a bad guy. That popped up when they were building dikes and created a real problem. The Village of Brown Station is here. The Winchell's Hill is here where the monument is. If you ever got up there and hiked the trail, the pathways, the monument's there. The main camp was here. There was another camp over on the south side down in this area. And over on the other side there, where they were building the dikes, there was a couple other camps. But this was the main camp where the majority of workers lived. The other interesting thing, if you can see the numbers, most of these contour lines are right around 500 feet, and you don't see too many popping up above that. And so the area was basically a glacial lake, and all the sediment that was in there came in as a result of the melting glaciers and filled up probably anywhere from 40 to 80 feet of mix from clay all the way up to sand and good topsoil. And so it was made for great farming. And I put a note in the bottom corner here. The upper basin is at 590 feet above sea level. The lower basin or east basin is of 3 feet lower. So when at full pool in both of them, you go dividing where there's 3-foot elevation difference between the two. Okay, so what happened? Then the workers had to have a lodging, and as near as I can figure, nothing is written about this, but all the camp buildings had to be built by Board of Water Supply. So they had, when the workers came in, they had places to live. There were dormitories or bunkhouses and all the support. There was a great big, what they call a commissary, a great big 2-story store. You could buy anything you wanted. There was has hospitals and engineers' offices. Everything they needed was built when the workers started to come in. And as the job grew, more and more workers came in. The interesting thing is when there were probably half of the workers on the job were Italians, hardly knew how to speak English or not at all. And they came up, were escorted up by a group from the city who knew them well, got them started with jobs, working. And in the evenings, I'm not sure who did, the contractor or Board of Water Supply, taught them English. So they all learned English. Worked out very well. But the first thing to do was to get the dams and dikes built. And I'm thinking that the dike work started at the same time as they started making the dam, but it just wasn't as glorious, so you didn't see too many pictures of that happening. Some of the supplied offices, the bank, nice building, it was started by a couple of people from the Brown Station area. The hospital had 3 nurses, a doctor, and an assistant doctor. That started off very low police protection, but it built up over time as more and more workers came on board. And the picture in the lower right is the contractors' office. I've not found a good picture of the engineering office, but they built their stuff was not defined where that was, and I haven't been able to locate it. Okay, the biggest job going was getting control of the stream. They built a Coffer Dam like this. There we go. Coffer Dam up here to make a quiet pool across here. And these are stanchions to hold 2 8-foot diameter, 400-foot long pipes that would carry the water flow. When pipes were in place, you're looking at the downstream side here and the upstream side here. And this is where the foundation of the dam was going to go. They had to dewater this area. Look close, there's a pipe going out of here where the pump is pulling water out of that portion of it. And all the time that they're building or digging down through bedrock, here you can see the compressed air hose. There was a number of compressors. They ran 80 PSI air to all these machines. No blasting, because they wanted this rock to come out as chunks, because here's a pile of them in the upper left. They made what was called Cyclopean Concrete, where when the dams were made out west in the early 40s and 30s, they were all cast concrete. Concrete, when it cures, gets hot. In order to get around that problem and be able to build up higher, faster, they used Cyclopean, where they used a fairly dry mix, put the stone in place. It was held in place by a derrick, slowly lowered it down, jogged it till it was there, settling into the mud, and it was solid. Then they would bring in more cement and put around it and hold that in place, and they would continue to build up that way. There were 2 reasons for that. It was quicker curing. It also had a locking place, because you really had no cross seams anywhere. You always had a lock a rock somewhere going up in elevation. So everything was locked together. So this is a dam that was built. The below sea level, or not below sea level, but low water level here. The stream ran at about 410 feet above sea level. The where'd my pointer go? Well, I'll just talk to it. The piece down at the lower part, on the lower left, at the toe of the heel of the dam, is what's called a cutoff. And they made that probably 40, 50 feet wide, and they dug down deep enough to where they were getting very little leakage through the rock strata. This being a glacial lake, and it was a glacial lake back 400 million years ago. That's how all that material turned into flat bluestone. There was no lifting or bending, and didn't look at all like the rock cut over on 209 going over the bridge. It's absolutely almost dead flat. So they were worried about any seepage down between the layers. So whenever there was a leak in the cutoff area, they would bore in, grout it, and stop that leak. So there was no visible means of leaking before they started the concrete work. And they continued to build up. As they built up, they packed soil around both sides of the dam. Can't see me from my finger. So and then the other part that they did, instead of forms, they cast concrete blocks. They must have had 50 different part numbers of blocks to get used. On the front of the dam, they had a 1x1, probably 45-degree slope. And as you go up further on the dam, it became more vertical. And the top of the dam on the back side, they were vertical blocks. They built drainage holes in it, as well as inspection ports. I gave this talk years back, about 3-4 years ago, to some of the guys at DEP. They said, yeah, they've been inside that dam. Not very exciting. You don't see anything. There's some little lights hanging out there. If you like caving, I think it would probably be interesting. I'm not particularly fond of that, so I'm not going in. This is some of the tools they used. The Winston Company, the prime contractor, moved power plants that he had over at the Catskill Dam. He finished the job there and he won this contract. And they brought over the flywheels. Now the UND complained that they were going to go out of business because they didn't have any shipping work when the dam was being worked on. Well, they hauled all this stuff up. Those flywheels came in 3 pieces and they were bolted together. Below, just above the word steam engine, is a dynamo for generating electricity. Each one of the systems had its own electricity, so they ran 110. I'm not sure if it was DC or AC, but they had lights, so they could work all around the clock. All the steam ran air compressors, and they pushed compressed air up to 2 miles over to the Yale quarry, so they could cut bluestone pieces that they used in the mortar mix. They also burned 1,400 tons of coal a month. Again, I'm not sure. Okay. Very touchy. They built a railroad, they being Winston and Company. This is all the track that they put in. The UND went across the top, around 3 miles. Over here, this is about the water line. Over here, we were hiking over here a couple of years ago. The embankments are still here, and the lines go over to the lines on the map went over to the quarry, and they had 2 areas. It's in the back, a picture in the back of the book. Concrete walls where the flat cars would go in between, and on the flat cars they carried a skip or a number of skips that they loaded the crushed rock in and carried that over to the cement plant. And that was an ongoing job, almost round the clock, carrying crushed rock over to make the mortar for all the work that they were doing. Okay, this is a cutoff trench. when they're down probably near the bottom. You can see the guys over on the right lifting some of the compressed air tubes out of the cut, and they're just a matter of cleaning up the bottom of it. And you can see the steps they made in the walls so that the concrete, the weight of the concrete would be kind of locked in place when it cured. It also acted as a form. Here's a picture of the Cyclopean concrete. The blurry spots you see on here are guys moving. The films back in the early 1900s were probably ASA of 5 when you look at the film speed. Anybody moving would be a blur. So you can see how the large boulders are dropped in place, and then if it wasn't cured yet, there was a post put by that boulder so that it would you wouldn't get near it until it was set, and they moved the posts off and then continued on up with the masonry. It looked disorganized, but as they built this, here you're still in the foundation of the dam, but they're working their way up. You can see the control tubes pipes are still in place. And then we're getting up near the top. The cutoff is over in the picture on the left, and you can see the gantry towers for the cableways that went across the dam. Those were key in building this thing. A company, Linderwood from Brooklyn, made these things, the control units, and it was up to the contractor to build the towers to put them on. And there was an operator in the ones that had the cabin on the top, and they were able to move the carrier at 1,000 feet per minute and carry 15 tons and drop it where they needed to. In the big picture, you can see a block in the middle, right in front of one of the tubes, and that's lowering in the first block to be set. This of the molded blocks, and they carried those over and put them in place, and that's starting would be the toe of the dam to work up to the top. Now, one of the puzzles I always had was how did they make the transition from the pipes to water flowing through the dam? Well, they had the Coffer Dam up at the top. They built the foundation up to the point where it was slightly above the stream flow. That's a 6-foot diameter pipe through here, right here. That's a 6-foot tube opening, and then a channel. And they called this piece an invert that was roughly 40 feet wide, and they made that higher. And then as they finished this end, the water flow would come across here, and there was enough curvature to the invert to carry the water flow through this. So then they could lift these tubes up. And they saved these tubes because they get used later. Now, the block yard was where all these things were made. They started 6 months before the contractor started work on the dam, making blocks. And again, I think these were not contractor people. They were probably Board of Water Supply, not employees, but a separate contract to make these blocks. They had forms where they would put the concrete on a steel plate to get the shape that they needed, and then they would let them dry and knock the frames apart, and with the derricks, pick up the blocks and store them in piles, and when they were ready to be used, they would put them on rail cars and run them over to the gantry cableways where they could be sent in place. So this gives you a great overview of what some of the work going on. All the soil that was dug up while they were digging, the guys on the post down the lower right-hand side are surveyors setting lines for the dam. The dam runs off to the right-hand side of the picture, and that light area in the far back is a pile of dried clay that they use for the embankments. Part of this job, 99% of the work from manpower seemed to be making these dikes, because we'll get into it a little further, but it's just a tremendous amount of work, hauling the soil out, sorting it out. Sand in some places, they needed that for the concrete, but the clay, the topsoil was saved in other piles. So the compressible materials that would go up against the core walls were all piled up to be able to use back again. Now here's the conduit as it's being built up. Now you'll notice, kind of hard to see from there, but there's no forms on the going into the water in the picture on the upper left. So it's some pretty tricky form work to build that so they can be able to put concrete over that arch without any water being or forms being held in the water at all, because the last thing you need is to have the formwork pushed out in the because of a flood. There's a picture in the book on the dividing weir showing a flood going through, and some of the formwork they had in that area all tangled up and washed up, and a whole bunch of guys standing there wondering, okay, what are we going to do today? And then a lower right picture shows the conduit pretty much complete. And this goes through the bottom of the dam. The trench at the bottom is about 410 feet above sea level, and the work up the dam is up to 600 feet high. Now, probably one of the more complex pictures, a lot going on here. You can see the formwork on end for the to cover the conduit. A lot of derricks in place to move blocks and material around, and more blocks in place over on the left-hand side waiting to be cemented in place. And the cableways on top, the travelers on the upper top, the second from the right, you can see a skip loaded with something coming back down over the dam. And these were probably the most, you'd never be able to build a dam without these things. There's no question about it. They ran almost 1,700 feet across the canyon. And the Esopus cut a fairly deep canyon through the bedrock of the valley. And you can see the blocks or skips probably looking at like they're full of concrete on rail cars waiting to be picked up and carried over to the dam for more cementing operation. And the insert at the lower left is the cement plant where all the cement was working. And that was two-shift operation all the time. Now this chart shows a little bit of detail of the dam. The horizontal dimension is half of what the vertical dimension is. That's why the conduit shows that to be an oval rather than the true a semicircle. But this shows a transition from the masonry dam, the block dam, to a wing where they ran wings on both ends of the dam. And they also built the dam from the south end to the north end, which is on the right. And they did it in sections. And these sections are expansion joints. This is the first dam in history that had expansion joints in it, both laterally and through the thickness of the dam. And the lines at the bottom show where the rock was at various times of the year. But they're basically boxes where each crew would work within a box and build their way up. And as they reached top of the dam elevation of 610 feet, that would be finished, ready for finishing, and the next box would come along and finish up, and we'll get into a little bit there. Okay, so at the end of 1910, they had 7 of the Liggerwood cableways. They were working on 4 in the dam. There was 1 over on the dividing weir, and they were a couple over on the dikes, where the only way you could make it, each one of the dike core walls were 1,000 feet long. So they put up forms and filled those with masonry. some big steam shovels. Most of the shovel work was done, again, moving earth for the embankments. And the rollers, same thing, to pack down the embankments. They put in a lot of new railroad track just primarily to move soil, move that material. They had a number of standard gauge and a whole lot of little narrow gauge dinky engines that were very busy. And at the end of 1910, there were over 4,000 guys working, lots of horses and mules. Didn't have pickup trucks or small things, so you had little dump trucks. So what you had was a four-wheel wagon and a black man with 3 mules. And the wagon had the capability of a lever option, and they could drop the load as he was going along and spread out the soil. And they used it a lot. They also ran, it's kind of hidden at the bottom, but they ran 3 shifts, 2 shifts of workers and 1 shift during the night of supplying more block to the work areas. So the guys that came in would have fresh material to work with. Another good look at the Cyclopean masonry being laid up. Again, this is the dam going up. You can see there isn't much masonry exposed as the dam is being built, and a lot of loose rock down at the bottom right-hand side, ready to be picked up by the derricks and lowered in place into the concrete. And you can see about in the middle was a hoist from the cableway dropping in either concrete or stone. Now, this is interesting. 42,000 barrels shipped in the month of June of cement for concrete. The Ashokan Dam, Ashokan plant is the same one that's up just above Catskill on the river. Different name, but they were still making cement back in those days. Now, there's a little confusion in some of the terminology. Everything is being shipped in barrels, yet in Lazarus White's book, who was one of the engineers who wrote a pretty good consensus of the whole Catskill project, said that cement came in bags. So I'm not sure who to agree with, but this said they were barrels. So now the conduit is getting higher up. You can see the slope of the conduit, and following up on the angle of the slope, you're still near the bottom of the dam, and how well the cableway will bring the materials out to the working area. This is sometime, I'm not sure if they're working yet or not. They work till probably just before Christmas every year. And there's snow on the ground, and there's a lot of water going through that conduit. Remember, that's a 40-foot wide opening. So there's quite a bit of water there. And you'll see some guys standing around looking at what's going on. So maybe they're just workers wondering, or engineers wondering what's happening with the storm. Now, this is a little bit more indication of the expansion joint. Normally, the blocks were laid in the classic running bond, 2 blocks down and a block across the top of that lay, so you get good adhesion. But when they came to the corner of the box, you can see, where's my pointer? There we are. Along here, you can look back to a little bit to the left and see the face of this box compared to that box. So there's no physical attachment other than grease. They put an inch of not very good Vaseline all the way across that to prevent the cement from attaching itself to this block. So each of these sections is basically free to move in its own fashion. Now, how much does concrete move? Probably not very much. But when you're building something that's over 1,000 feet long, you're going to get some lateral motion. Now, this is a drawing of that Waldo Smith came up with You're looking on the left-hand side is the upstream side of the dam, the water side. And follow that across to the right, you'll see different size blocks made to act as keys into each of the sections. So each one of these boxes are very solidly made into the concrete, but there's no physical connection of cement to the next box, which would be up at top. Then there's a well for any drainage that gets in through that might leak down through the grease, and then into the well it would go away. So nothing leaks out the front of the dam. You probably in your travels have seen a dam where the face might have mold growing on it, green a little bit every once in a while. That's from a leak, a crack in the dam, the water slowly going through it. Waldo Smith said it's not going to happen at my dam, and it sure didn't. Now you can see the black line. The insert is the same, just a blow up of the same picture, but the black line is about an inch thick layer of grease put against the concrete, and then as they built the dam up with masonry, the masonry went against the grease and cured and dried, but there was a layer of motion that could be absorbed in that grease, so that if something did expand, a real long heat wave or real cold period, there would be probably micro inches of movement in that area. The other thing you might notice on the lower picture, about in the middle, there's a rack. The dam is getting kind of narrow at the top, so there isn't room on top to hold all the rock and everything that they're working with. So there's a platform there. So the cableways at night would drop a number of layers of rock on there so they can move it over into position to use during the day. Now this is the top. I flipped the picture on the right to match up with the drawing that's on the right. Typically, there's no place on the dam where the curve would be on that's on the downstream side, but he's not. He would be on actually looking to the southeast. But the top is 610 feet high, with pavement on the top, drainage holes put into the upper expansion or inspection galley. And you can see the different shapes of block that's used as they're stacking it up. Larger block tied into, again, lock the masonry into the body of the dam, so everything is one cohesive piece of masonry when they're done. And here's a view of the workers getting close to the south end of the dam. You can see the steepness of the slope on the right-hand side. And then this will be a transition area where there'll be a core wall and a wing that goes back a couple hundred feet, almost 1,000 feet on this end, and not quite as far on the north end. Now, to close up the conduit, in the design of the block, there's no picture other than just a description of it. There's about a foot-long deep cavity behind the forms to allow cement or masonry to lock in, so it's not just a skim coat. And so it's maybe about a 2 foot wide opening that goes around the opening on the inside. And the wall block there is probably close to 10 foot wide. So that form is pushing up against the outside one with a gap of about somewhere in the 10 foot range from what I've been able to read. And the figures you see on here give you an idea of the size of the opening that you're closing up. And it took a steady pour overnight from starting early in the morning till overnight until middle of the next day of steady work, bringing masonry from the plant by cableway, horse, mule wagon, and then another derrick to fill the forms from the outside. Now you'll notice too, on the bottom here, there's two big stanchions built, and you're looking at the top of the 6-foot diameter tube that's in the bottom of the dam. That will ultimately be closed on September 13th of 1913 to actually start storing water. So there's a picture of the top of the dam where they managed to finish it, running an engine across, and they carried a lot of fill. You can see the embankment over on the left-hand side of the top picture with the shape of the fill, and that's all top dressed with topsoil ready for grassing. And another picture, and in the lower picture down here, you can see a darker gray block, newer block that finished the opening here. It took probably close to a year with a whole team of guys and a cement plant down here making concrete and block to go in and fill that hole. Because you're looking at probably 300 foot of dam through here. It's a lot of material that had to get filled up. So there's some numbers. Time allotted was 84 months. The other thing that threw people off was that there was a change from a 10-hour workday to an 8-hour workday at pretty much the beginning of the work period. So it added more time, and that's I think why they put the second shift on. But I want you to think about the material. 426,000 cubic yards of Cyclopean masonry. The football field is 5,330 square yards. So divide 5,300 into 46,000, that's like about 80 football fields covered a cubic yard deep or a yard deep with masonry. Same way with the cast blocks. So there's a lot of materials that were used, and they came in for the dam itself a little bit cheaper. Now the dividing weir was another big job. Actually, the dikes. They were down to bedrock, and they protected with earth fill with bluestone on the water side. If you've ever been up there, again, all by hand, and the fill was moved with whatever way they could do it the most effectively. The dikes were built. Here's the dividing weir. This is a dike between here and the main dam. There are dikes all along here. If you go up the reservoir and you park in this little curved parking lot here, that's about 1.5 miles long. There's a dike here. Then you go over here, there's a dike. And there's a dike here. This is the Westerly dike, and the Woodstock dike and Glenford dike over here. There's the camps were over here, this area as well. Here's the Beaverkill Gorge. Now this was another gorge that was fogged out by the melting glaciers and then filled in with silt and materials as the glacier melted and eroded away a lot of rock and whatever else that it came in. So it gives you an idea. That's 80 foot deep and about 40, 50 foot wide at the bottom that they hogged out. And the soil was so hard at the bottom, they had to use jackhammers to break that loose to get a good bond between the concrete and the bedrock. And there's the top, a picture of the Beaverkill. They called it Beaverkill dike for a whole long time, then changed it to the middle dike as they started going around. But the gorge was just to the left of the railroad tracks. That's the UND tracks going through the area at the time. And you can get an idea how much fill is being added. And the fill was dropped over the sides in the area, raked out by hand. The rocks were brought to the outboard side, and the water side was rolled every 4 inches to 80% the hardness of concrete. And on the grass side, it was rolled every 6 inches. So that's why they needed so many rollers. Again, continuing on with the dikes, the cableway was a great way to bring on skips full of soil to fill against the dikes. And they built a 1,000-foot length of dike with an opening in between. And then they joined that with a special short section, again, digging down to bedrock and building this up. So no water was going to leak through these dikes. Here you're looking in the upper left, the Woodstock dike. This is now part of the rail trail. And then on the embankment of the west dike, just outside of Brown Station, if you go across the dividing weir and walk this little section that goes over towards the island or the mainland where the Winchell's Hill is, this is a piece of the dike you're walking on. Now, this is the only picture I found of this. This came out of New York Public Library. It's an interesting thing. They go to their picture section and you put in just about any word you want. And you type in Ashokan, you get all kinds of great images that are free to use. And this is one of the Board of Water Supply engineers watching to see the work get done. And these poor folks are getting a load of bluestone pieces, standing them on end, stacking up from below the water, well below the water line to 10 feet above the water line to protect the inner side of the dikes from erosion due to wave action and ice. Big, big, big job when you figure there's 6 miles of dikes. So to move the Delaware and Hudson Railroad, they originally, Kuykendall said, it's going to cost $4.5 million for property damages and all, trying to hold up the Board of Water Supply for more money. And he had the law on his side because you could not disturb a railroad property until the claim is settled. But in June 15th of 1911, they did agree to $2.5 million, $2.8 million. And the contractor doing the work rather than having Kuykendall have them do the work. So they built the dikes, they moved the railroad tracks, and Kuykendall could keep running his trains. They had special tunnels built through the dikes, so the train came through the west dike, around through Brown Station, back up through the Beaverkill dike or the middle dike, and then over to the West Hurley end through that dike. And they all had big openings. Here in the center is the old rail track right of way and the new right of way at the top. These are the passages that had to be built through the tunnels. The question is why it's so wide? Well, that's the width that they had to cover for all the fill that had to go over the railroad tracks, not just the concrete. So they had to go back with a 1 on 2 foot out for every foot up. They had to go quite a ways back to make tunnels that they could pack fill over. And then when the when the railroad was moved, they could collapse that inward and pack it, and they had that completed. This was a bridge over a cut where they moved water for the water from the intake for a conference of mayors back in the I think 1910. So now there are two basins, the upper and lower, east and west. The maps I'll call the east and west. I think most of the locals call them upper and lower basins. But the upper basin always had a problem with dirty water. So they any dirty water like that would come down from the Ashokan would be collected and settled in the west basin, and then the east basin would get good clean water. And that's where most of the water gets drawn off that goes down into the aqueduct, even though they're twin controllers. So again, same way with the dikes, down to bedrock and build up the masonry structures to support the roadway. This is a great picture. I bid on this originally on eBay, and I was beat out at $80. But it's a picture you don't see very often. I end up getting it another time. But you can see the earth being dumped off of these cars. These are unique vehicles because they're able to hold a load balanced, and then they can be tipped with a lever on either side of the track. And up in the Delaware Valley, they found one of these rail cars back in the woods and hauled it out, and haven't yet restored it, but that was a picture from a few years ago. But you can see the mule drivers. They all came from the south. There's nobody up in the valley knew how to drive mules. Winston had a mule farm. By the way, Winston Farms in Saugerties, same Winston was the contractor. He raised a lot of mules and a lot of horses just to supply the demand here. And I'm sure he charged for them. There was a little bit of segregation. The black folks all had their own camp, or at least part of the camp, where they stayed together. And the interesting thing, many of the black mule drivers that came north all came with sidearms, which was kind of a surprise. I don't know if anybody was actually shot. Somebody mentioned the question about deaths on the job. That was very difficult to find. A friend of mine works for Kaiser Funeral Parlor, and they had the coroner's or the list of all the bodies that were brought in over the timeline that the reservoir was done. There wasn't a single reservoir body that the person from Kaiser's who was the coroner had listed. Come to find out, it was New York state law that back in the late 1800s buried all the death certificates, so from an accidental death. So you couldn't find out what happened to any of these people. So there was actually zero deaths found by anybody who worked on the reservoir. The New York State said at the end of the project, of all their projects going on for the Catskill water supply, there were a little over 300 deaths for everything, for the aqueducts, all the reservoirs down the line to the city. So, which is pretty unique. Okay, midway through, they put a lot of extensive form work in to build the roads and the bridges. And here's in the middle picture is the intake tunnel for the water from the East Basin and from the West Basin. You can see water standing in the West Basin. And then there's a steam train going down, bringing fill in to work on the lower part of the dividing weir. Following on, the cableways were invaluable to work over a big span like this, primarily moving concrete. But they did include in the conduit for this power and phone cables when it was built. Okay, this is a top view of the headworks. The gate chambers are here. Remember when you drive across the dividing weir, there's the two big buildings. There are gate valves inside there. They dug trenches. This one is probably close to a half mile long through rock. This one's a lot less down to the basin. So water could flow into the lower gate openings of the gates. And then the water went from here down through high pressure tubes. That's actually those same pipes that you saw earlier for the diversion pipes tubes, and into the lower gate chamber where the pressure was reduced, and then it fed into the aeration basin. the output from here went either into the basin, collected, and then out through the screen chamber, and then into the aqueduct, or down through the waste channel into the lower Esopus Creek that we get every once in a while. The dividing weir has at low water, you can see a wall that runs down along here. There's a couple of sluice gates here. There's 4 that allow water to be transferred directly from the upper basin to the lower basin. The only other way is just spillover water that comes down over each of the gates. This is looking at the gatehouses, the upper and lower, or the east and west gatehouses. They're twins. And this is the dike, same process built as the other one, except underneath the water flows through 2 buried pipes. Where's my pointer go? There we go. Here, and then they're backfilled with Cyclopean concrete before the dividing wall. And these are go through the rock, and where they break out through the end of the wall, they are cut into 2 tubes that are brought out through the pipes, through valves, and then into the pipes. And here's the sluice gates in operation. Then that, again, the only way to go between the upper and lower basins. And the intent with the aerator was to improve water quality and kill organisms by UV light from the sunlight. And today the water goes down to Croton Reservoir where it's chlorinated. There were 1,518 bronze fountains. I have no idea whatever happened to those when they took them out in the mid-70s. They put a small power generation plant there in the middle of the water flow. And a couple of pictures of the plumbing necessary to handle the nozzles and make that work. This is an early picture of the basin. Many of you have been up the reservoir, have driven down this road. Some of the guys in this room have run up this road, and some of the runs that the Your Runners Club did. And this is the final result with the spray going out of the aerators. Now, just a little bit of the tools that they used. Lots of mule wagons. These are the Eagle wagons that are used as dump wagons. They can just drop the soil and keep right on moving. So they can really handy to have. Upper picture there was the mule barns. These are a couple of tractors. In the digging I did for the book, tried to find what each of these manufacturers were. This lower stump puller, that vehicle was the precursor of the Caterpillar tractor family company. And the up here, the traction engine, this was used a couple of places along the reservoir and on the aqueducts, not to any great advantage. It was get bogged down in muddy, soft ground. It was far easier and cheaper to lay down a narrow gauge railway and run little dinky engines 4 or 5 miles to where they had to go than to run these traction engines. They were big, they were heavy, and they couldn't pull real good loads. Steam shovels, again, the major job in these guys was just moving earth from where it was to where they want it to be so they can put it down for the embankments. And same with the railroads, both standard gauge and narrow gauge. As I mentioned, those dump cars are quite unique in their design. They stay balanced around corners and all, and you pull a lever and they can dump either right or left, depending on where the work is being done. The going over to the trestle, going over the Esopus Canyon to the Yale Quarry and back again. Top end train is empty going up. It's about a 2.5% grade. Engines can't pull much more than a 3. And this is a standard gauge. And then coming back down, pushing the load of bluestone. the Lingerwood cableways were just magnificent in what they can do and the work that they've done. Company is still partly in existence, tied in with a company out of Superior, Wisconsin, but they still offer these kinds of equipment. Concrete mixers and stone crushers were all over the place. That had to be the god-awful noisiest place you could imagine when they were in full operation, with a giant stone crusher at the cement plant. They had the rock would be crushed down to about fist size to be used in the masonry, and they had crushers over at the quarry, a couple of the quarries. They had this big one and a couple of other little ones wherever they needed a concrete plant. And the derricks were all built on site. In the book, I have an ad that I saw on eBay and had to buy it about the American Hoist Company advertising that their hoisting engines, which are, come on, there we go, right here, used to pull the cables at the wire ropes that go up to lift the loads on the derricks. They're rotated by hand, but are lifted by the hoisting engine. And we saw the fixed equipment. This is the main power plant where they burn the coal to make the steam to turn all the compressors. And it looks like the dynamo with the vapor around here is turned by steam. So the contractors, the buildings were made, I think, again, by a subcontractor prior to the workers getting on site. And $20 a month with meals. And the camp supported up to 4,000 people. There's a little booklet I picked up again on eBay about a woman who wrote what it was like to be a teenage girl at the camp. And one of the fun things we're doing, at 4 o'clock in the evening, the whistle would blow. And just a couple of minutes before that, the mules knew it was about time to stop working. And one would bray, then they all started braying. And the drivers had a heck of a time controlling them. They ended up standing up on the wagons after they dumped their loads, heading back to the mule barn. They said it was a race to be, if you were in the way, you were in trouble. But most of them were Italian, European immigrants, few Irish. But then the police force grew naturally, as one would expect. Camps were interesting. They were well put together. They were well outfitted. They all had a kitchen, wood stove, and a cook stove, and a privy, right? See the arrow point? There's a little privy out here. The plumbing is such that the water from the house will go through the concrete privy, down the sewer line to a massive sewer plant with a giant septic system. So they handled the cleanliness and everything very well. And the people lived there in winter. The book I have in back called Ashokan mentions in there that that was a book I found years ago, never used it, seldom opened it, and started reading it and found more things about what life was like in the camps than I found anywhere else in anybody's book. So I had it reprinted, and there's some copies back there. But the contractor or Board of Water Supply, I'm not sure which, supplied wood to all the cabins for heat in the wintertime. And people just didn't pick up and go to Florida in the wintertime like they do around here. So you just kind of stuck it out. And I can imagine back in the early 1900s what winters in Ashokan were like. They were probably a lot colder than they are today. But they also came by and picked up the ashes and took care of the trash. So it was very well maintained. Payday. These are starting salaries, and they're fairly small numbers. They're a little bit more extensive than what's in the book, but this was a 6-day work week. That changed not long after that started. Police officers, they probably had, the New York City Police, the best horsemen and around. There are so many pictures of them. One guy standing on each horse and a third person standing on top of the shoulders of the two horsemen. But they had wonderful little bicycles, and you notice the bicycle, the vehicle on the left looked like a little gasoline powered motorcycle. The surveyors are probably the toughest breed of guys that I can imagine, because they surveyed that entire 12 square miles into 5-foot contour lines, identified all the soils that were all within that, sand pits, clay, whatever it was, they identified the soil into types of use. The farriers and the people that worked in these fixed industries for the contractor, I think, came along with Winston and Company when they moved up from the Catskill Reservoir. Same with the engine train drivers. The guy with the on the left with the white shirt on is probably the engineer of the dinky. The other guy is the fireman, and the guy, this is the state of the New York Board of Water Supply guy with the train orders. Go here, and they're running back and forth, moving soil or whatever. And the mule wagons, same thing. There's a lot going on up there. They had a Y, Boy Scout troops. The town of West Ashokan had the first 3 Eagle Scouts in New York State. That was before the reservoir came in, which was quite interesting. And they also had a lot of ball teams. They had the workers had a team. The Board of Water Supply employees had a baseball team, and they fought for trophies quite regularly. And the water boy, there's a lady, Diane Galusha, wrote a book called Waterworks, which was an excellent book all about the New York City water system. Catskill Reservoir was one of them. Had a picture of this young boy. She interviewed or pulled a paper. They had an interview. They worked for 10 cents a day hauling water around the workers. And the guy who was probably in his 80s when he did the interview said he gave the money to his mother because there was no place to go for no corner store or anything to spend his money on. And then on Saturdays and Sundays, time off. I'm not sure the bigger picture, if that's on site or not. The site was dry. There's no alcohol on the site. If you were caught with alcohol, you were fired. So that was one good reason to, I think a lot of the accidents were preventable. But these guys look like they were carrying empty beer bottles, so that may have been off site. And the pictures in the book, and you look closely, you can see the guys are holding playing cards. And that was not really accepted practice. Now this picture is of a clam bake that the Board of Water Supply had for their guys. I want you to notice the 2 guys in back right. One guy in a zoot suit, and the guy a little bit older, dressed with a hat and jacket. They're not going to party with the guys on Saturday and August 28th. They're heading into Kingston. The book has a timetable, and just about every 2 hours, there's a train that left Brown Station, and in about 30 minutes, you're in Kingston. Coming back, it's about 35 minutes because they had to pull the hill. But for about $1 round trip, you could go into Kingston and do whatever you wanted to do. Now, the wrap up, the basin was sealed in the 13th. They had a celebration on the top of the dam, and the menu was, if I can read this here, fried chicken. I liked it. It starts off with pickles, and they served beer, so that was a good day. And it was a typical October morning or day where drizzly rain, and The guys in the suits are naturally the big guns of the operation. And it was held at the top of the dam. So here's what happened over long run. $7 million underestimate. They purchased 2,800 parcels, cost originally 176 million. And they had to add a police force, and it cost them a bunch more for the 8-hour day. But they also put in a second shift, which helped a lot. A couple of good books. The Studing's Last of the Handmade Dams. It's out of print, but you can find it around here a lot. Liquid Assets is Diane Galush's book. It's excellent. The Water for a City, that's out of print, but it's he talks a lot about the Ramapo Water District, the water company, and the work being done prior to the Board of Water Supply getting into it, and then what happened. In this book, Old Westerly Revisited, it's a self-published thing that talks a lot about leaving Kingston, taking a half a day to horse and buggy to get up to West Hurley, and all the things they saw about in West Hurley. It's an interesting little booklet. And a couple of webs. The New York Public Library is a great place for if you want to look at pictures. And this DVD, Deep Water, Toby Carey did that probably 10 years ago. You can get it at most libraries and look at it. It's really interesting. And this is an aerial view. I don't know where I found this, but it gives you a little bit of a view of concept. The main dam is over here, and the dividing weir here. Oh, one thing I forgot, I started to talk about the beaver kill. That went down through. They had to do the same thing with that beaver kill dike underneath the dividing weir, not the dividing weir, but the core wall, as they did with the main dam. They had to put a tunnel in it and let the water flow through it until they were done with the dam. Then they could seal that up and let that water go into the lower basin. But it was that 80-foot deep gorge was something they did not consider, but they could do a good work around. So that's it. Any questions? I'm sorry it took so long. Technology doesn't always work the way we want it to.
There's a question from chat. How did they measure turbidity when the dam was done?
That's certainly not the way they do today. I'm not sure. I have no idea. I'm not sure they probably had means of doing it, but I just don't know. They probably had a lab up there, and they probably by centrifuging the water and measuring the sediment in the bottom of the sample tubes. I'm guessing. Anything in the room?
The aqueducts were being built simultaneously.
Oh, absolutely. Yeah, they when they sealed the dam in 13, they started water going through the aqueduct. The aqueduct, I dropped a book off with Adam Bosch at DEP today. We got talking about the aqueduct, and that's more technology involved in that aqueduct than there is anything in here, because it's all hard rock mining. And a lot of it's cut and cover.
Mm-hmm.
But in many places, there's 3 siphon tunnels under the Rondout Creek, under the Hudson, and one other lower creek where they had to go through, where they had to go down. Under the Hudson, they went down 1,400 feet below sea level.
Wow.
And they dug 14-foot diameter, big enough for a 14-foot diameter tube to go through. And in High Falls, they went 6 miles of underground mining from the Rondout Creek east. They went down west of the Rondout Creek, under the creek with a siphon tunnel, then back up below grade, because if they didn't go below grade and come back up at the end of the mountain, they would have to have the pipe elevated, something like 60, 70 feet. That's impossible. So they had to go down underground. They blew out. The rock wasn't solid enough where they put in the down tube to go in. It wasn't strong enough to hold the water pressure behind it and blew out. So they had to spend close to a year and a half developing a shunt method to fix the steel pipe. They made 120 degree arcs of steel, kind of like a bent U-channel. Lowered them down these shafts. Now these shafts were rinky-dink outfits. I have pictures of all the shafts, and they're like ropes on the lifting engines, of course, but they're just like ropes going down with guys standing in the bucket. Very few in the bucket, all of them hanging on the riding down on the outside of the bucket. They had to lower these sections down in, line them up, and fasten them together into a ring underground. I don't know if they developed arc welding there or they learned how to use it to a great advantage. Naturally, couldn't use any flame welding underground,
Right.
but they had the DC electricity. So they arc welded these rings every 2 feet to the inside of the steel tube to support it. Then they went through and concreted over the top of that. So they reduced the diameter of the pipe a little bit, but it cut back a bit on the flow of water, but it wasn't significant. But that made the pipe strong enough so that the water pressure at that point would not cause it to blow out.
Right.
Yeah.
So another question from chat. Is any of this work built or building available on video to show local students? Are there any newsreels or anything else of that nature of construction?
Not really. The work was done from probably, 1907 to around 1910, 1911, where they finished up. There might have been some old hand crank movies, but there got to be so many people wandering through the construction site that in 1909, the Board of Water Supply just shut the site down to visitors. They fenced it in, they put guards on the gates. In fact, a lot of the people, the workers that stayed in the camps used to go out to the vendors that were outside the gates. They'd come through the camps selling stuff. And that worked fine, but then they closed down the site, so the vendors had to set up site, and the only time on weekends they were there. So the workers could go out there and buy stuff from them. Anything else?
So I just know from reading, the amazing thing is there's not one pump in the whole system from
All gravity fed.
Ashokan all the way to the city.
All gravity fed.
All gravity.
And it was interesting, for the last 2 years in the summers, they closed the aqueduct and had guys cleaning it. They built tubes. The aqueduct has an invert, probably about 14 feet across. And then there's walls where it's more than about 15 feet high. And they run maybe 10, 11 feet of water in that. It's not full under pressure, just gravity fed. And it's probably about a slope of about 1 to 2 feet per mile. So it's not a lot of slope. But they found there's some algae that forms on the inside of some bacteria that forms on the inside that slows the water down. So they went in and cleaned it and found they've raised the water flow, water resistance against the sidewall by maybe 10%, so they can actually move more water through the system than they thought they could get back to the 500 million gallons a day. Yeah, it's a remarkable operation.
Are you talking about the aqueduct that they replaced under the Hudson recently?
No, that comes out of the Delaware River,
Okay.
the Delaware Aqueduct. That was built after World War II. And they hurried up to do that one, and they're nowhere near the quality of work that goes in here. I mentioned earlier at the Yale Quarry, there's 2 big concrete not block walls, but laid up bluestone walls where they ran the flat cars with skips on between them and loaded it with the crushed stone. There is no loose rock in that cement work. And that was 110 years ago. We were there maybe 2 years ago and wandered around there. There's a great trail if you go over to the bottom of the reservoir on the bottom of the south wing. There's a parking area right along 28A. And there's just a short trail, maybe half a mile into the Yale Quarry. And you can see that the stanchions where the rock crusher was in these walls. Took a while to figure out what they were, but Dr. Roberts, who's involved with the Friends of Historic Things, and I have poked around places together, and it's kind of fun to try and figure out what's going on there. But the railroad embankment goes right along the road, cuts through there.